So hopefully I didn't fool you with any of these answers. One thing to notice is that because these are all supposed to be forces on the right cart, or in other words on cart 2, the second subscript must be 2 for all of them. And so that also tells you, for example, that A can't be right because it's mentioning a contact force on the track. No, all of these have to be forces on cart 2. And so the correct answer here is D. Now let's move on to the other effective forces on objects that we are going to pay attention to in this course, which is deformation of objects. So first I just want to remind you that that's one of the things that forces do, but second of all, I want to tell you why we're interested in it. We're interested in it because often the way we know that a force is acting on an object is that the object is deformed. And similarly, the amount of deformation of the object can often tell us how strong the force is that acts on it. I'm going to start with springs, and the reason I'm starting with springs is that springs give you visual feedback about the forces on them. So a spring that is neither stretched nor compressed is what we might call relaxed, and it has some relaxed length that's a property of the spring. If you pull on the spring, then it stretches, and you can feel it pulling back on your hand. Notice that the force I've put on that diagram is the force that the spring is exerting on your hand. That, of course, is part of an interaction pair with the force that your hand is exerting on the spring. Notice that that force by the spring on your hand is pulling back towards where the end of the spring would be if it was at its relaxed length. If you push on the spring instead of pulling on it, then you can feel it pushing back on you. And again, the force that the spring is exerting on your hand is pointing back towards where the end would be if the spring was at its relaxed length. So because these forces that the spring is exerting always point back towards its relaxed length, we call these restoring forces. The other way of thinking of them is that the force exerted by the spring is always in the opposite direction to the displacement vector of the end of the spring. Another key thing about the forces that springs exert is that they depend on how much you stretch the spring. If you only pull a little bit, then the spring will exert a relatively small force back on your hand. But if you stretch it out more, it'll exert a stronger force. Similarly, if you compress it more, that also makes the push that it exerts back on your hand larger. Now suppose you have a spring that's standing vertically on the floor. If you take a brick and slowly and gently lower it onto the spring, then the spring will compress until the point where the brick is held stationary, and at that point it stops compressing and everything is in equilibrium. Similarly, if you hang the spring from a ceiling and then somehow hang the brick from it, again slowly and gently, the spring will stretch until the brick is held stationary. Because the spring is supporting the brick in either case, we might call this a support force. And notice that in both cases what we have for the brick is that it has a downward gravitational force due to the Earth and an upward contact force due to the spring. And because it's being held stationary, so its acceleration is 0, we know that those two forces are equal in magnitude. But also notice that that means the free body diagram looks exactly the same for both cases. Of course, not all springs are the same, and the main characteristic for our purposes that distinguishes them is something called the stiffness. Just looking at the picture, you can probably already tell what the difference is between a stiff spring and a less stiff spring, or what we might call a soft spring. And for comparison, I'm going to compare them both with a post. Suppose we put a brick now on each one. All three can support the brick. The stiff spring has had to compress to do so, and the soft spring has had to compress more. But note, all three bricks are stationary, and so the acceleration is 0, and so all three of these support forces are just equal to the gravitational force on the brick. So the soft spring, stiff spring, and post all exert the same support force. The difference is that the soft spring has had to deform much more to be able to provide a force that large. The post doesn't appear to have deformed at all, but in fact if you do very careful measurements, you would find that the post has compressed just a little bit. We can do the same comparison with hanging springs, and we'll compare them to a rope or maybe a cable. Again, if you hang bricks off of them, the stiff spring is going to deform to be able to provide the support force. The soft spring will deform more. The rope will not deform much at all. It's hard to notice that it's stretched, but it will have stretched a little bit. The fact that the post and the rope also deform like springs, but like very, very stiff springs, is part of the fact that basically everything around you behaves like this. So when you sit in a chair, the chair deforms, it compresses under you. That's obvious when you sit in a big poofy armchair, less obvious with a steel chair, but it still happens. Similarly, when you're standing, the bottoms of your feet compress. That's easy to see. It's harder to see that the floor also compresses and flexes, although if you live in an old house with creaky floors, you certainly know, but it even happens with concrete floors. The force exerted by a spring is a function of the amount of deformation of the spring, and since we've just seen that everything is basically a spring, this is true for every other object as well. That can be very useful if you know this function that connects the deformation to the force exerted, because if you know the amount of deformation, now you can find the force exerted from it. Or conversely, if you know the force exerted, you can find the amount of deformation. Think of how useful that is if you're doing something like designing a bridge.